Hello, my name is Age of Valencia, and today I'll present to you a research on extracting device fingerprints from flash memory. In short, this paper evaluates 7 techniques for extracting unique signatures from NAND flash memory, in which 4 were identified as effective methods. Aside from what I mentioned, why do we want to know about this? Why is it important? But before I dive into that, let me tell you the important things to know about this study. As I mentioned, it's about extracting device fingerprints from flash memory. To begin with, flash memory is a non-volatile storage used in storages no different from your SSDs, USBs, or even your smartphones. Now, it's important to know it's arranged in a hierarchical order, but think of a chip as a library holding information for the flash memory. The block is like the bookshelf holding these pages, and the page is the data written on the block. And fingerprints, also known as signatures, probably not like the fingerprints you thought when you read the title of this presentation, but these are more of like the unique device-specific patterns extracted from the flash memory due to the natural variations from creation, sort of like real fingerprints. Lastly, the PUF, or physically unclonable function hardware, feature is a uniquely based on physical variation occurring during the manufacturing, such as things like transistor delay or electrical resistance. Now that we have all the important things established, I do want to discuss why flash memory fingerprinting. Why is it important to even know about this? Firstly, some things to know is that everyday people like me and you buy USBs, SD cards, SSDs, and things of the matter. Flash memory fingerprint can verify authenticity, ensuring people get genuine, reliable products. More reasons as to why we should know about this is that it enhances security in our smartphones and devices through the unique fingerprinting, preventing things like tampering and stolen devices. Lastly, I want to mention devices can authenticate themselves based on flash fingerprinting, preventing fraud and enhanced communications. Firstly, to identify counterfeit flash chips, counterfeit meaning the act of making these fake copies of these flash memory devices, device manufacturers would extract the signature from the flash device and mark it with a serial number. Then, purchasers use flash-based memory, FPUF, to extract the signature for that address, and the FPUF is used to extract a unique identifier to bind it to that device. With that out the way, it's important to know that FPUFs must meet 4 criteria to be considered useful. They should be fast in the manner that they generate signatures quick for manufacturing, not cause significant damage, such as they should degrade the flash memory and reliability, have a low false positive rate in the case of mistakenly matching 2 different ones, and lastly, intractable to forge, in a manner that a counterfeiter should not be able to replicate or predict a device's fingerprint, ensuring that security is against cloning. Next, I'll go into some applications of FPUFs. Now, imagine this. You're trying to buy a Rolex, right? But obviously, you don't want to buy a fake one, right? Though, when you want to buy one, there are counterfeiters that flood the market to sell fake Rolexes with cheaper materials that malfunction quickly. But to resolve this problem, Rolex could embed a microscopic engraving to check if the engraving with the genuine serial number checks out, then if they don't match, then the watch is fake. Same situation as the picture shown here. Manufacturers can verify the chip if it's authentic or counterfeit, ensuring trusted devices are used in computing systems. Essentially, FPUFs help prevent counterfeit chips from infiltrating the supply chains, introducing security risks. Now, I want to ask, have you ever questioned your own handwriting with someone else's? Well, flash memory chips have their own handwritten signatures too. Due to tiny manufacturing imperfections, no 2 chips are exactly the same. In many modern-day devices like smartphones, laptops, and IoT gadgets, they rely on memory for storage. Because every flash memory chip has a unique physical variation, we can use FPUFs to create hardware-based identifiers for each device. If a system has low-level access to the flash chip, it can extract FPUF signature and use it for authentication. In short, FPUFs turn every flash memory chip into a unique clonable fingerprint for device security. One thing to note is that random numbers are essential for encryption, secure communication, and cybersecurity applications. In relevance to flash-based physically unclonable functions, FPUFs, they provide a hardware-based source of randomness by exploiting natural variations in flash memory. Next, to understand flash chips, I'll discuss the characteristics of flash memory. So, flash memory stores data using floating gate transistors which trap electrical charges to represent bits with NAND gates, with NAND flash arranging multiple transistors in chain for high density storage. Now, I know that's a lot to wrap your head around, but think of this as multiple transistors connected to a chain, and to move these electrons through this gate, they have to tunnel it. Some flash devices use multi-level cells to store multiple bits, others use single-level cells. The main idea, though, is that these characteristics impact performance, durability, and security for fingerprint extracting. Another characteristic is the organization of the memory. Flash memory is organized into arrays of thousands of flash chains grouped into blocks efficient for reading, writing, and programming, where each block has 16,000 to 32,000 chains, with data stored in pages connected by a word line. Some important operations to know are read, write, program, and erase operations, the same as coding, but the data is to and from memory cells. While program and while read and program operations happen at the page level, erase operations affect entire blocks. And one thing to note is that due to capacitive coupling, repeated programs like read and program can cause bit errors in adjacent cells over time. Understanding variations is critical for optimizing flash memory performance. One thing to note is that if flash memory cells are closely packed together, small variations in geometry or oxide thickness is impactful. These variations can affect individual and behavioral intercell interactions like capacity coupling, previously mentioned. Since these variations are random, it can result in unique latency operations and unreliable fingerprints. One thing it does, it makes me wonder is if the temperature and possible voltage fluctuations can affect the data. I wonder if even the endurance of the flash memory is affected too, but that's another topic. Now I want to go into data collection hardware. To explain how flash chips are analyzed in the study, I'll briefly explain how it's done. To extract signatures from flash devices, a testing board contains two flash chip test sockets. This board connects a Xilinx XUP board running Linux. The system accesses the flash memory through a custom-built flash board controller running on the FPGA, shown in this slide right here. This then allows the team to send operations to the device at will. So, here are some of the parameters for the 27 flash devices used in this study. As we can see, there are different manufacturers, page sizes, and pages per block. The set of the chips' varied geometry is the result of the previously mentioned topics from manufacturing processes, cell types, firmware, all the way to array organization. In all, these affect their speed, endurance, reliability, and cost. Though, going deeper into the criteria, FPUFs should be able to differentiate differentiate between chips with high confidence. Signatures from two devices should vary randomly from another. At the same time, they should be robust in that repeatedly extracting from same devices should be very similar, if not identical. Also, FPUFs should be fast. Some applications require extracting a signature from every flash chip from an assembly line. If it takes hours, that means it's not practical. They should also be difficult to forge results. FPUFs must be infeasible or impossible for the counterfeiter to forge the signature. It shouldn't be possible to store the signature on the chip and replay it when the chip detects that an FPUF is applied. If applying an FPUF, it should not significantly damage the chip. If FPUFs render part of the chip usable, it will not be useful. Now, to describe how cells responds to the program disturb mentioned previously, it's critical to know how it works and what it is. Program disturb occurs when programming one flash memory cell unintentionally affects the behavior of nearby physically adjacent cells. This is usually due to capacitive coupling or other physical phenomena within the memory array. The program disturb typically happens because flash memory cells are packed tightly together to maximize storage density. Now, briefly, I want to portray the algorithm at sort of a higher level for extracting program signatures. It checks for program disturbed induced bit errors in an adjacent page and records the cycle number at which each bit error occurs to create a unique program disturbed signature for the device. Essentially, this is important because it helps identify and characterize variations in the behavior of flash memory devices, enabling FPUFs that can be used for reliability assessment and improving security in the memory's performance. Now, before I show the signature correlations, in this study, a correlation metric was used to measure the robustness of signatures and their ability to uniquely identify flash devices. The Pearson measures the correlation between two sets of data with values close to 1. In flash memory, it's used to compare program-based signatures from different pages. Now, previously mentioned are the 27 flash devices here shown in the graphs. The graph on the left shows extracting disturbed signatures from the same page, and the right graph shows extracting program disturbance signatures from different pages. The Pearson correlation helps assess the robustness and uniqueness of the signatures. Now, why is this important to know? It shows that the signatures extracted from the same page are highly correlated, meaning that repeated extractions from the same page or block produce similar results despite their inherent noise. Now, this is crucial to know because it confirms that program disturbed signatures can reliably represent the physical characteristics even with randomness. And also, for a side note, the correlation for the left plot is 0.94 and the right plot has a correlation of 0.012. Now, for the right plot, the correlations are not high because it shows the program disturbs effects vary between devices. The low correlation is crucial for uniqueness because it indicates that each device has a distinct program disturb signature, allowing for reliable device identification. And in essence, high correlations mean program disturb based signatures is reliable and consistent when extracted multiple times from the same device. It shows that despite the noise, the process of extracting signature yields reproducible results for the same device, important for ensuring accuracy and stability for the device's fingerprint. This study is important because it shows that the program disturbed-based signatures is a viable method which can be used for device identification and authentication. Moreover, extending this analysis to a larger population of devices is shown on this graph. This graph illustrates the selectivity of the program disturb-based signature. This study particularly extracted signatures from one block for 10 chips, BMLC125, BSLC1-5. Essentially, the histogram shows the distribution of statistical correlation of all pairs of signatures, including signatures from the same block. The white bars are from the same chip, while the black bars are from pairings of two different chips. The large gap between the distribution shows program disturbed signatures can reliably differentiate between different chips, demonstrating the likelihood of false positive rates. Now, I do want to highlight the importance and key takeaways from this study that I found is crucial is that by testing the method across various flash chips, the study highlights selectivity, scalability, and efficiency for the technique of device authentication and security. The results are crucial for ensuring robust device identification in large-scale applications like IoT and data centers, where distinguishing between devices is essential for security and the trade-off between signature strength and latency must be carefully managed. In this case study, this demonstrates how increasing number of program operations improves the ability of program disturb-based signatures to reliably distinguish between different flash devices. The key highlight, though, is that we can essentially reduce latency and sacrifice some of the signature's power by limiting the number of program operations. We can see the effect changing the number of operations on the gap between the signatures from the same chip and the ones from different chips. In this case, each line represents a different pair of signatures from BMLC 1-5. The solid lines are mismatched pairs. And upon looking at the data here, number of operations is less than 4,500. The signatures do not reliably distinguish between the devices, but by 5,000 they can do so reliably. In this figure, I would like to highlight also how after a certain point of around 5,000 operations, further increasing the number of operations offers diminishing returns in accuracy and significantly increases the extraction time. Therefore, Approximately 5,000 operations strike a balance between speed, an extraction time of 50 seconds, and reliability, making it an efficient choice for device identification. Next, I want to discuss forging a chip's signature. In order for a counterfeiter to forge a chip's signature, the person would need to store the signature information inside the flash chip, detect attempts to extract a signature, and replay the signature back in response. Extracting a program disturbed signature requires an unusual and easy to detect access pattern, so replaying the signature is a definite danger. Now, another study tested is the feasibility of forging flash chip signatures by quantizing them. Even with 4 values, the signature required 2 bits per flash bit, and to store it, it couldn't be compressed. This makes forgery impractical. The study also confirmed that signature extraction doesn't degrade the chip, ensuring its security and integrity. Next, I do want to break down how FPUF extracts signatures. FPUF essentially, it extracts signatures using read disturb. First, the entire block is erased, then programmed with random data. Next, each page in the block is read millions of times to induce read disturb. And every 1,000 read iterations, errors are checked for each page, and if an error is found, the bit is recorded, the page number is recorded, as well as a cycle number in the error within that error. This process is repeated 10 million times. The final signature consists of the read cycle counts for all bits in the block, which are used to uniquely identify the flash device. Now, this method focuses on capturing variations in cell behavior caused by read disturb. And once again, you're probably wondering why this is even relevant to even know. Well, it's important to know this because it shows how read disturb based signatures can be used to create unique identifiers for each flash device, even in the presence of external factors. This method provides an additional layer of robustness against forgery and counterfeiting, making it harder for attackers to replicate or tamper with the device's signature. And by ensuring that each device has a unique read disturb based signature, it becomes harder for counterfeit devices to infiltrate the market. Next, I want to discuss read disturb signatures comparisons. Now, compared to program disturbed signatures, read disturbed signatures are less noisy with correlations between multiple signatures from the same block, averaging approximately 0.98. Correlations between signatures from the different blocks were extremely low, being around 0 for the test chips. Now, I do want to mention that the correlations near 1 indicate signatures from 2 flash devices are highly similar, meaning they most likely originate from the same device, while on the other hand, 0 suggests that signatures are different, meaning they cannot be easily confused with one another. In essence, higher correlations is better for authenticity checks. Just a little side note. Though one thing worth noting is that the main disadvantage of the read disturb technique is that it's slow, such that it can take 6 hours to extract useful signatures from MLC chips. SLC chips are less susceptible to read disturb, so useful signatures were not extracted from any of the SLC chips. This also kind of makes me wonder if a high density MLC chip could take even longer to extract signatures from. Anyways, next, this technique is less resistant to counterfeiters than the program disturb technique. Basically, quantizing signatures to just a single bit provides correlations bigger than 0.98, and also storing all signatures on a forged chip could be less feasible, that is, less than 70 bits. Though I will say extracting this kind of signature is non-destructive since read operations do not move charge on or off of the floating gate. Next, I'll discuss 2 FPUFs which use per bit variation and program latency to create a signature. In the test, 2 variations of latency signatures are tested, that being single page and multi-page. The main idea of them is that the single page version program each bit in a single bit page within a block operations with a program starting at 0 followed by 1s, and then a second program of 2 zeros followed by 1s, and then so on and so forth. As for the multi-page program, there's an nth bit, so the programs are spread across all pages in the block, and after a certain number of programs, the entire block is erased to make sure the program goes to an empty page. Each cell has a single measurement of latency values, assuring the desired signature. In this study, two single-level cell chips and two multi-level cell chips were extracted of their signatures. On the left, for the SLC devices, just 100 per bit program latency measurements give correlations over zero point 0.8 and provide good selectivity. As for the right graph, the MLC devices, there are 100 measurements which also give good results, and selectivity decreases the number of measurement rises. Now, if that was just gibberish, essentially for single level cell chips, a small number of measurements is enough to get reliable uniqueness. And for multi-level cell chips, too many measurements reduce selectivity, making smaller signatures more effective. And essentially, the key takeaways is that SLC chips generate strong selective signatures with minimal measurements, and MLC chips suffer from systematic variations, making excessive measurements counterproductive. Essentially, smaller signatures work better. But in a bigger view, I envision this impacts cybersecurity, supply chain integrity, and like maybe anti-counterfeiting efforts in electronics, ensuring that critical infrastructure and consumer devices remain authentic. The main drawback of this technique is that the information content of the signatures is pretty low. The latency measurements taken on these were approximately 20 discrete values, so storing each just takes a few bits. Since smaller signatures are preferable for this technique, forging these signatures will be easier. Signature generation is, however, very quick and causes almost no wear in the device, as it takes 1 to 3 seconds to generate 1,000 measurement signatures, and the process takes a single program erase cycle to extract a signature from a block. Some things I do want to get into are potential sources for flash chips, but were not examined as the researchers of this study found that it turned out to be not useful, and here are the four listed on the screen right now. First, there's erase latency, which is essentially the time it takes to erase a block, though this was proved ineffective due to the low variation and inconsistency across blocks. Next, we have read latency, which measures essentially how long it takes to read a page. This was ineffective in the manner that the read nearly constant across all the devices, especially for the single level cell chips. As for the third source, whole page program latency, this is the time it takes to program an entire page as a signature. This is proved to be ineffective due to the lack of variation between pages and devices. And lastly, the potential signature, which turned out to be not useful, is the program/erase wear technique. This technique measures how cells degrade over repeated and program/erase cycles, and it turned out to be too slow, taking hours, and essentially damaging as it rendered blocks unusable. Also, it made it easy for forgers to detect and bypass avoiding known signature blocks. Essentially, these alternative signature methods were found to be unreliable due to low variation, inconsistency, or ease of forgery, highlighting the need for more robust and tamper-resistant techniques for authenticating flash memory devices. In this table, we can see the results of the flash memory physically unclonable functions (FPUFs) research in the study. It portrays the range of values measured for the gap correlation values comparing signatures from the same chip and different chips, the time it required to extract a signature, the number of bits per signature, and finally the number of programs and erase cycles extracting a signature requires. In this table, the results show the FPUFs based on the program disturb and program latencies are most useful. Essentially, program disturb was the most effective in distinguishing chips. It's also highly information dense but had a long extraction time. Program latency provided the fastest useful method, making it ideal for large-scale manufacturing applications. And looking at read-disturb FPUF's numbers, they provide highly accurate signatures, but the time for them is too slow with approximately 24 hours of extraction time. Some ineffective methods also include erase latency, read latency, and whole page program latency, as they showed little variations or were very easy to forge. Now, the key takeaway is the program disturb and program latency FPUFs offer the best balance between accuracy and practicality for secure chip authentication. Now, to conclude, this study explored 7 different flash physical unclonable function FPUFs for extracting unique signatures from flash memory devices. Through extensive testing on 13 different flash chips, 4 of these techniques demonstrated reliability, each offering trade offs in speed, selectivity, durability, and resistance to forgery. The findings highlight that flash based FPUFs can serve as a robust method for uniquely identifying and authenticating electronic devices, enhancing hardware security against counterfeiting and unauthorized modifications. Though, one question I do had lingering is how can the integration of FPUFs into large scale manufacturing processes improve supply chain security without introducing significant performance overhead? Though I think that's more of a thought that will present itself more in like the long run. Anyways, lastly, I do want to conclude though that as threats to hardware security continue to evolve, leveraging intrinsic physical properties like FPUFs presents a promising path forward. The challenge now, though, I think lies more in optimizing these techniques for real world deployment while balancing security, efficiency, and scalability. Lastly, here's my works cited page for some information I gathered from this research aside from the actual book itself that I cited here. And lastly, to conclude my presentation, I'd like to thank you all for your time and attention. Thank you.